Just about any stage starting from first year in engineering or science, we all get involved in labs where we have to take measurements, and such measurements can be physical quantities or electrical, such as the examples that are shown in the slides to follow. The main thing is none of us ever really take into consideration that the measurement that we take, or rather the measurement that we read off the screen, can be very far wrong from what it really should be, because many factors such as calibration of the device, the way we use the device, etc. So we're going to take a look at how something as simple as uncertainty in calibration can affect a simple measurement. The idea here is more to demonstrate a concept and not complicate things. A measurement is basically an attempt at physically quantifying a parameter. It could be length or distance. It could be voltage. It could be current. It could be quantity in liters. It could be quantity in kilograms, or any one of these things, or many other things as well. The process of measurement, instead of going about it in an abstract theoretical manner, I will take a simple experiment and look at a single measurement. For instance, we have some kind of an electrical circuit. It doesn't matter what the electrical circuit is. And using a multimeter, we are going to measure the current and the voltage at one section of the electrical circuit. It could be at a point or it could be at a couple of points. Using the measured data of current and voltage, we're going to try and calculate the power in watts, which is an exercise which most of us perform in ET lab in early stages of our engineering education. How does lack of reliability in measuring the current and voltage affect the end result of power? Let's take a look. What are the components of measurements? We have the circuit board. It doesn't matter what circuit it is. A multimeter. The same multimeter has voltage and current. We need, as we will find out a little later, a power source, which will be usually a good calibrated precision power supply. We also need a calculator for doing multiplication, particularly since decimal places will be involved. So, having said all this, let's look at the measurement. If we switch on the circuit, apply the power supply to it, and we measure the current and voltage at a specific place in the electrical circuit. For purpose of discussion, let us just say the following are the readings we got: 22.7 volts and 2.3 amps. This is what has been read off the multimeter screen and noted down. Where can the source of trouble be? Each one of these readings, both the voltage and the current, have to be calibrated against a precision supply to verify that when you say 22.7 volts, for example, you mean 22.7 volts, or you will have a range within which the point can be. Even though you say 22.7, it could be any point in a given range. So we need to look at the calibration certificate for the multimeter. We are not going to worry much about the precision power supply for now. I'll explain that later. But there are much more exotic problems possible in a measurement. But right now we're just going to keep it simple. We're going to look at what happens if we don't have calibration data. If a calibration has been done, typically there would be a certificate available that says the measurement uncertainty is so much. If we are measuring up to the first decimal place, then we will probably calibrate to the second decimal place. In case no calibration data is available, we can quickly check the meter by taking the precision power supply, which is hopefully calibrated, and take 3 quick measurements and do a linear regression on it. We have now verified the calibration certificate on the multimeter, and we have found that the accuracy of the voltage reading is 20 to 30 volt range plus or minus 0.13 volts. Similarly, the accuracy of the current in the 1 to 5 amp range is plus or minus 0.1 amps. So what this says to us is the voltage reading that we have taken as 22.7 volts could be anywhere from 22.57 to 22.83. The current reading, which you have noted down as 2.3, can be anything from 2.2 to 2.4. Any point on that range of 0.26 volts in the voltage and zero point 0.2 amps in the current is equally valid as any other point. Let's look at the effect of these 6 readings. When you look at the table of maximum minimum possible, you find that the range of calculated result in power can be from 49.65 to 54.79 if the uncertainty is as given in the calibration records of the voltmeter for voltage and current meter for current. This is the level of uncertainty that you will face in the power output calculations. We find that the total range of the power is around 5.14 watts. Based on the measurement and calculation basis, this is about just under 10% of the measured calculated value. This is not a good result because acceptable levels of error in measurements should be around 3% ideally. What we have done essentially is a rather simplistic procedure for estimating uncertainty in measurements. It is based more on common sense and less on proven technology or mathematics. This is given a fairly accurate range within which our measurements ought to be. There are much more complex and in-depth procedures that are available. What we are trying to do here is to be able to have readings that are reliable. That is only possible when the numbers have credibility, and that is only possible when the numbers, the calibration data, can be traced to international primary standards. Such calibrations are done in places like National Physical Laboratory in Delhi, whose branch office is Fluid Control Research Institute in Palakkad near Coimbatore. These two places do a lot of such calibrations for a fee, of course. Such calibrations can be an expensive proposition. So what we can do is to take certain primary standards. For instance, if you calibrate the precision power supply and keep it properly in calibration and maintain the record of the calibration and recalibrate it every time the validity of the calibration is about to expire, that itself can suffice to help us do the calibration for other things. Multimeters are used at home and in labs, and the calibration of a multimeter can be disturbed just by dropping the multimeter on the floor. It need not break. Just by dropping it, it can change. Or using old batteries inside the multimeter, or changing the leads from one multimeter to another, because the leads have set resistance values, and if you change them, end result is going to differ even if microscopically. If we do not have a calibration for the multimeter, the best thing is to do a quick calibration so that we reduce the uncertainty as much as possible. Since we are working with 23 volts range, so we should look at either say 18, 23 and 28, or 10, 20 and 30. Take these 3 points, connect up the voltage side channel of the multimeter to the precision power supply, and take readings after setting the precision power supply for these 3 values. Once you get the readings, you got 3 points on a graph sheet. You can do a linear regression and you will have a relationship y is equal to ax plus b type, which can be used to correct all your readings. So this is sort of like a quick cal. Calibration and traceability is not cheap. And that is why I recommend identifying logically certain apparatuses in the lab and keeping them in calibration. For instance, you keep a precision power supply, you can calibrate all the multimeters, oscilloscopes, everything. Similarly, you keep one box of primary weights, you can calibrate all your balances. Like that, it's easy to identify 3 or 4 primary devices and keep them in calibration so that the rest of the equipment in the laboratory can be calibrated using these primaries.